Hello, ECE 341 students. This is Dr. Vladimir Goncharov with a review of homework number 1 assignment. As we talked about in lecture on Friday, these 3 dice are non-standard. Instead of having numbers 1 through 6 on each of the 6 faces, they've got these different arrangements, many repetitions, and even though they have the same average value, when you roll them, turns out they have some surprising properties. When you play head-to-head rolling one die against another die, for example. So let's take a look at what's asked for in this assignment. First of all, assume that each of the 6 faces is equally likely to occur when you roll a die. So that's called a fair die. And that when you roll one die, the result is independent of rolling any other die, including the same one. So that means there's no memory effect. Again, a property of having what they call a fair die. Okay, so if we call italicized A the outcome of rolling die A, then the outcome can have values either 3 or 6, but 3 occurs with 5/6 probability and 6 occurs with 1/6 probability because there are only 6 possible outcomes and they're equally likely. The way I showed in class is by performing the experiment of rolling die A, therefore there will be 2 possible outcomes. These are they, 3 and a 6, and 3 occurs with probability 5/6, 6 with probability 1/6. Now we can repeat this for the other 2 dies, but let's concentrate on die A for the moment. You are asked to come up with the mean value of the outcome of rolling die A. That is the average value. And this is skipping ahead a little bit in class, but I think the concept is quite simple. You take the outcome value, which is 3, and you weighted average with this outcome value, which is 6, the only 2 possible outcomes. And the weights that you use for the averaging add up to 1, and they are the probabilities of each of the 2 outcomes, because essentially this forms an event space. You've got event 3 or event 6, and they are mutually exclusive and collectively exhaustive. So 5/6, the probability of getting a 3 times 3, plus 1/6, the probability of getting a 6 times 6, is the calculation that needs to take place in order to calculate the mean value of A. 15/6 plus 6/6 is 21/6, or 7.5. I should say 7/2. I know the answer, sorry. 7/2. So let's take a look at the questions that follow, because the first part is easy now. You're asked to calculate the probability values, for example, that rolling die A will give you an outcome that's less than that of rolling die B. Once I go through this, it'll be very easy to solve every one of those. By the way, no 2 dice have the same numbers on them, so therefore all of these will be 0. I just threw that in there for completeness sake because that could have been an outcome. That's probable, but here it has 0 probability. Okay, so let's take a look at what's the probability of A being less than B when we roll the 2 dice. To do that, let me draw another tree for B so we can see what outcomes it has. And this time I won't calculate its mean value. I'll just draw the 2 outcomes, and 3 out of 6 times it's 2, so that would be 3/6 or 1/2 probability of occurring, and 3 out of 6 outcomes is a 5, or again 1/2 probability of occurring. If we perform an experiment that we roll both dice together, it may be combined into a single tree diagram as follows. Let's say we roll die A first. So I'll write this A equals 3, and here A equals 6 are the two outcomes of rolling die A. This occurs with probability 5, 6. This occurs with probability 1, 6, and that's what we had previously. Now, if we follow up by rolling die B, when A had landed on a 3, and we know that rolling B is really independent of what happened here, we'll get the same statistics as we had previously for B. That is, B equals to 2 occurs with probability 1/2. B equals to 5 also occurs with probability 1/2. Same thing here. If we follow up on the outcome that A is equal to 6 and roll die B, it will be 2 and 5 with 50-50 chance of occurring, so that's 1/2 probability each. And now we've drawn a tree diagram whereby it describes all outcomes of this experiment. Let me summarize this outcome. This outcome is that A equals 3, and that is greater than B equals 2. Here we have A equals 3, which is less than B equals 5. Here we have A equals 6, greater than B equals to 2, and A equals 6, greater than B equals 5. If you count or calculate the probabilities of each of these occurring, it's simply going down and multiplying the probabilities along the paths of the tree. So that's 5, 6 times 1/2, 5/12 probability. Again, 5/12, and 1/12 for the remaining two outcomes. When you're all done, all of these probabilities should add up to 1 because it describes, again, a sample space. And it's true, they add up to 1. Now let me highlight those that correspond to the case that we're interested in, and that is the probability that A is greater than B. That would include this event right here, this event, and this event. All but one of those joint outcomes is the situation where A is greater than B. Therefore, the probability that A is greater than B is equal to 5/12, the probability of this outcome, plus 1/12 plus 1/12. 7/12. All right? And you were asked to do this for all the essentially 6 possibilities. Because equality of the outcomes is not possible, all of these will be 0 in the middle column. That means that probability A less than B is the complement of the event probability A greater than B. In effect, you only have to do 3 calculations. We saw that this is 7/12, so this must be 5/12, and so on. Okay, so that's part B. Now let's think about what we need to do for parts C and D. Now it's a little more complicated. Label AA as the result that you get when you roll A twice and you add together the outcomes. What is the mean value? Okay, so it's kind of similar to what we had here, except now you're rolling A and rolling A again. Let me